Good evening, everybody. My name is Konrad. I'm a hydrologist with the U.S. Geological Survey. I am here tonight, though, not in my professional capacity, which means I can actually speak a little more freely about some issues. I want to clarify, too, I am not a geologist. I am trained as a civil engineer, so I come at hydrology from a perspective of kind of more what's happening today, tomorrow, yesterday, as opposed to 10,000, 100,000, millions of years ago. So if you ask me, if you have questions about kind of those types of timescales, I probably would just have to guess. So just to be clear about that. Tonight, we've got a couple of ground rules. One, the purpose for this talk is for us to talk about water. So ask me questions, and if you want me to clarify something, just ask me to clarify it as I go along. That's totally legit and encouraged. And also no equations. So no equations tonight. There are a couple of numbers, but no equations. So when Bridger asked me to talk tonight, he specifically asked me to talk about water and bedrock. And I said I could, but you know, the problem with it is it's a very technical topic, and so it's hard to say a lot about it without getting super technical. So my goal tonight is to keep it conceptual and make it understandable. And again, so if people need some clarification, just feel free to ask me. So with that, let's get going. So an overview of what I'll talk about tonight. We'll talk about geologic materials that hold water. We call those aquifers. And we'll talk about a couple of different types of aquifers, the kind of the major types of aquifers here in the valley. We'll talk about something called porosity. So that's one kind of technical term, not too scary though. Then we'll really kind of launch into bedrock aquifers, talk about water levels in those aquifers. We'll talk about recharge, talk about wells, and then we'll end with a little bit of a discussion about management, which hopefully will get people riled up. And and again, I have no kind of professional duties as far as water management goes. I'm just a scientist. So I'd be happy to share my personal opinions, but I can't really help anybody with if they have water management issues. Okay, so let's start with geology. And again, caveat, I'm not a geologist. I have taken a couple of geology classes. The first geology class I took was Geology of the Grand Canyon, and I did it because for spring break we went to the Grand Canyon. And so I know just enough to kind of, you know, get by during a dinner party or at a bar, but I would never speak professionally about geology. But we need to at least be clear about a couple of things with geology. So we have consolidated rocks, that's bedrock, and we have unconsolidated sediments, right? So sediments fill up the Methow Valley, and then the consolidated rocks make the valley walls and the mountaintops. You see unconsolidated stuff filling in here, and there'll be terraces along the side of the walls that are unconsolidated, so sand and gravel. The consolidated rocks are either going to be igneous, and then igneous rocks that have been metamorphosized, so they've been changed under heat and pressure, so that's things like granite, gneiss, and schist. And then we also have sedimentary rocks that have been metamorphosized, so they're rocks that then have been pressed and heated. And so those are sandstone, shale, conglomerate, and slate. And I use this picture in particular because it's pretty interesting. This is Grizzly Mountain right here. It's going to be like a granodiorite, a granite igneous rock that basically is formed under the earth, and then it pushes up as a solid material over time. Right here is Winthrop sandstone, and you can kind of see these lines right here. So there probably used to be a whole lot of sandstone covering all these rocks, But when glaciers came through and carved out the valley, they eroded most of that material away. So part of tonight, is hopefully folks can kind of think about where they live and what of this talk relates to you personally. Maybe a good place to start is, well, what's the geology of where you live or where you like to be? And you may not know, so the first thing to do is think about kind of landforms. So are you on hillsides, which are typically going to be bedrock? There might be some sand and gravel kind of over the bedrock, but really the hillside itself is going to be mostly bedrock. Here's a terrace, so you have a flat surface right here, and this is all going to be sand and gravel. The valley fill is going to be typically sand and gravel. So if you know kind of these different landforms, you can probably get a good guess of what your geology is. Rock type, or what we say is lithology, can also be visible at outcrops. So there may be outcrops nearby to where you live, and that'll give you a sense of like what the rock is where you live. And then also well logs. When wells are drilled, the driller will basically keep a log of the different layers that they encounter as they go down. And that's their interpretation, so it could be wrong or it could be kind of close to what it is. But anyway, it's still a good source of information. And you may, if you've had a well drilled, you should have gotten a well log. If you don't have a well log, but you have a well, you can go to this website that the Department of Ecology has, and they've actually pulled together all the different well logs that they have, and you can actually go online, there'll be a map, you can click on the place where you live, and you might be able to find your well log there, and there'll be like I'm not sure if it's a JPEG or an image, PDF of the well log, and you'll see what the driller encountered as they were drilling down. Okay, so big overview on geology. When we were interested in water and rocks, then we really have to start talking about aquifers. Aquifers are just geologic materials that hold or store water. So rocks and sediment that store water, that's all an aquifer is. There are different types of materials, as I mentioned. There's consolidated material, rock, and then unconsolidated material, so sediments, that's silt, sand, gravel. So I'll be talking a lot about consolidated aquifers, but here in the valley, we also have lots of unconsolidated aquifers that are very important, and they interact with bedrock aquifers. So we'll talk about those a little bit too. So we talk about aquifers based on the type of material. The other way that we talk about aquifers is based on hydraulic conditions. So that's the water in the aquifer. And that water can either be unconfined, which means that the water table can kind of go up and down freely. There's nothing constraining it other than the volume of water that's being stored. So we call that an unconfined aquifer. There's some impermeable unit at the bottom of that aquifer that's holding the water in there, but the water table can go up and down depending on how much water is being stored in the aquifer. So the other type of aquifer is a confined aquifer, and that's an aquifer that has a cap essentially over the top of it. And so the water table can only go up to that cap. You can build up pressure in the aquifer, so if you put a well in, the water level in the well could be higher than the water in the aquifer itself, because the well is telling you how much pressure is in that aquifer. Talk more about that as we go along. Either type of aquifer, consolidated or unconsolidated, can be confined or unconfined. So we got 4 different possibilities here, just to kind of keep track of things, right? So often consolidated aquifers are confined Often unconsolidated aquifers are unconfined, but that's not always the case. And you don't have to remember this, so don't worry about it. Okay, so that's major types of aquifers: confined, unconfined, and then that's the hydraulic condition, and then the material that the aquifer is made out of can either be rock or sand and gravel. When we characterize an aquifer, a really important thing is its porosity, which is the fraction of an aquifer's volume that can hold water. So if you imagine a glass filled with ice, you can still pour water in that, right? And so however much water you can pour into that glass before the water overflows, that's telling you about the porosity of the glass. Aquifer works the same way. It has space, air, voids, and that space will hold water. And the way we talk about that is talk about porosity, and we express it as a percent of the volume. Typically, in fractured rock, the porosity is between 0 or a very small amount and 10% of the volume. So if you were able to like chunk out a cubic yard of fractured rock, you would have 1/10 of a cubic yard of space that it could hold water. Sand and gravel, the porosity is much higher. It's about 1/4 of the volume, or even as much as 1/2 of the volume. There's nuance here in terms of like you can't get all the water out of all the space, but we don't need to worry about that. Generally, the bottom line here is that there's a lot less space in fractured rock, so a given volume of a rock aquifer is going to hold less water than a sand or gravel aquifer. Okay, so we got kind of these big concepts about different types of aquifers, how much water they generally can hold. Now when we start looking at groundwater here in the Methow, we kind of can get a little more specific. So the source of groundwater here is precipitation. There's no, as far as we know, there's no kind of mysterious conduits coming from the Okanagan or from Lake Chelan or from somewhere else that water flows into the basin from. So groundwater is coming from precipitation, so snowmelt and rain. We talk about recharge, which is when you have snowmelt or stream flow or rain that flows down into an aquifer, so that's what recharge is. That water is stored in the aquifer, and then it can discharge from springs, can seep back into the rivers, and then wells also are another way that we get water kind of out of the groundwater system. And groundwater is affected by geology and elevation, as geology, as I mentioned before. And then elevation is important because we see a lot of the precipitation is at higher elevations. So the recharge is going to be at higher elevations. The water flows down. So these areas here are going to get recharged by precipitation and recharged kind of higher up in the basin. So it isn't the case that everything's local. We do have these processes that are occurring kind of over distances, and that's why we can get some kind of unusual situations where you might be in some bedrock and it may be that water is being recharged from a mountain, some distance away, but that's above you. Okay, so I'm going to talk briefly about how groundwater discharges or where groundwater discharges. So we have springs and seeps. In hydrology, we talk about this as groundwater surface water interactions. So essentially we have groundwater that's then coming back out into the land surface. And the places that happens, we call springs or seeps. And these are really important for maintaining perennial stream flow. They also maintain cold water in rivers during the summer, and they prevent rivers and streams from freezing in the winter. So springs and seeps are really important for rivers and streams. And an important distinction here between the different types of aquifers is that water can seep out of unconsolidated aquifers, so sand and gravel that fills the valley, over very long distances. And for example, from Goat Creek down to the Big Valley, there's water that seeps into the Methow, groundwater that seeps into the Methow, so we're talking, miles. But in bedrock, you're only going to see springs where there are cracks. And so that means that if the water level in that bedrock isn't right at that crack, then you aren't going to get that spring, or that spring's going to dry up. So springs in bedrock can be much more sensitive than seepage from unconsolidated aquifers. Okay, so let's talk a little bit more about these two different aquifer types, unconfined aquifers. As I mentioned, we've got a bunch of sand and gravel here that's filled up with water up to this point. We call this the water table right here. And if we put in a couple of wells here, we're going to see the water levels in the wells are going to be right at the water table. And the water table goes up and down, and that basically gives us a measure of how much water is being stored in that aquifer, right? You can see, like, if the water table dropped in half, you'd have half as much water stored in the aquifer. Water table gives us lots of good information about aquifer storage, and you basically, in order to get the water table to drop that much, you would have to pump out this much volume of water. So that's all that's easy to figure out. One thing I want to mention before we talk about confined aquifers is that even though these wells are open at different depths, the water levels in them are the same. And that's because the water level in the well, or the water level in the well, is basically telling you about the height or the elevation of the opening of the well and the pressure at that point. So as you go deeper in this aquifer, you're going to have higher water pressure because there's water above. And so even though this opening is further down, you have more pressure, so the water level is going to be the same. Okay, so we have to kind of know both the water table, elevation, but then when we have a well, the well isn't just open at the water table, it's actually open down here, and then pressure pushes the water up to this level. So, unconfined aquifer. In a confined aquifer, so like, this shows kind of a sediment or a unconsolidated confined aquifer, but same thing would be true for a bedrock aquifer. When we have a confining unit here, then the water table can only, or the water can only come up to the bottom of this unit, but there can still be pressure in the aquifer so that when we put a well in, we see a water level up here. If we have this well over here, though, that doesn't even get through the confining unit, it's going to be dry. So two wells very close to each other, really different situations. And so the key here is that we have a confining unit in a confined aquifer, low permeability, water essentially can't move very quickly through this unit, and that allows pressure to build up in this unit. Yeah, so is that, folks, pretty clear on that? Okay, so we'll move on to bedrock aquifers. So they can either extend to the land surface, as I showed in that earlier diagram, or often they can be underneath an unconsolidated aquifer. So here we have some unconsolidated sediments like the valley bottom. Underneath all those sediments, there's actually bedrock that has cracks in it, and there'll be some water in that as well. The key with the bedrock aquifers is that the water is located in cracks rather than in the pores or the spaces between, you know, the sand and gravel grains. As I mentioned, porosity is much lower in a bedrock aquifer. So at most, maybe 10%, but it's probably going to be a lot less than 10% of the volume of this aquifer can actually hold water. In a lot of cases, these bedrock aquifers are confined, so the water is maybe under pressure. And that's important when we start, when we get interested in kind of how much water can we get from an aquifer and what happens when we start to the water levels when we start pumping an aquifer. Because water under pressure, you don't have to pump it very much to like reduce that pressure and then drop that water level, even though you haven't extracted very much water. So that's the confined aquifer situation. With an unconfined aquifer, you only lower this water level if you are actually dewatering the sediments. It's not just a matter of like relieving the pressure. You're actually having to withdraw the water to drop the water level. When you get down into a confined aquifer, all you have to do is basically reduce the pressure and the water level is going to drop. Okay, so bedrock, how do bedrock aquifers, how do we recharge water? Well, it depends on a source of water, and so that's going to be snowpack, it's going to be streams, water seeps out of streams into bedrock. It can be soil, so if you have nice thick soils that hold water, that water slowly drains into the bedrock, or sediments that are over the bedrock. So any of those can be sources of recharge. Recharge comes from higher elevations through cracks that are connected. And then aquifers that are connected to high elevation recharge zones can have very high water pressures. So if we are, if there are cracks that connect, the mountain down to this area here, you can see very high pressures down here because of that connection. In this figure, an important thing to note is like, okay, so we've got snowpack in the mountains, we've got snowpack here, snow melt from that snowpack is recharging aquifers. Here we don't have any snowpack, so even though there could be recharge if there was snowpack, there's not. So we're not getting recharge in these places. So if you kind of look out at the landscape, in the spring, and you see places where there's no snowpack, there could be some recharge from the water that's in the soil there, but it's not going to be as much as if you see a bunch of snow that's melting. Okay, so this is some figures from this study that we did 20 years ago looking at irrigation canal seepage. And the bottom line was we did see water coming out of the irrigation canals. It only happens during the irrigation season, obviously, because that's only when there is water in the canals. And that water kind of comes back into the river. In this case, the Twist River we're looking at. That process, as soon as the canals shut off in the fall, it takes a couple of months, and then there's no more recharge that's coming back into the aquifer, and there's no more water coming back into the river. So it's a very kind of transient, short-term process. But that's not really why we're here or what I wanted to talk about with this particular slide. What I wanted to talk about was that the water levels in bedrock aquifers is much more sensitive to recharge because the water levels are telling us about water pressure, not just about water volume. And so we did this investigation. This is the Twist River here. This is the TVIP ditch. This is the MVID ditch. This is Poor Man Creek right here. There's a big terrace right here. We had a series of wells, monitoring wells, to try to look at groundwater recharge from the ditch and then see how it was coming back into the river. And I'm going to show you a hydrograph, this plot down here, from this well, and then we had a water level recorder in the river. So the water level recorder in the river is blue, and so this is Twist River water level from May 2001 to October 2002. You know, as you expect, we see snow melt, summer low flow, winter pretty stable, snow melt, and again fall or late summer, fall, low flow. So blue line is the river level. Red line is actually before I do the red line, let's do brown line is a well that is in an unconfined aquifer. So that's very close to the river, this well right here. You can see basically the water levels there kind of track the river. So we're seeing water levels coming up, probably in response to river recharge of the aquifer, and then coming back down. The red line shows the water levels in a bedrock aquifer right at the edge of the terrace. So this is that big terrace up the Twist Valley. And you can see that basically during the irrigation season, water levels come way up. So this is about 6 feet. They come up and then drop back down and then come back up. Now, the important thing to recognize here is that this doesn't just represent the volume of water that's being stored in that aquifer. It actually represents pressure because the ditch is up here. It's probably, gosh, maybe not 100 feet, but it might be close to 100 feet above this well. And so there's a lot of pressure, and that's what a lot of this response is a pressure response. And so what that means is that in this bedrock aquifer, water levels can rise really dramatically in response to recharge. They can fall really dramatically in response to pumping or when you stop recharge. And that sensitivity is important because if your well opening is right in here, then there's going to be times when your well's dry. Okay, water yield. So that's just what we were talking about is kind of water, how much water do we get out of an aquifer? And we measure it with something called water yield. And typically what we'll do is we'll say, okay, how much water do we get for, a foot or a meter, whatever units you like, change in water level. So if the water's here, drops down a foot, how much water volume do we get from that? And confined bedrock aquifers with low porosity, unconnected cracks, have low yield, and then water levels that are very sensitive to recharge and pumping. Unconfined and unconsolidated aquifers that extend over large areas, they will yield a lot of water and and that's just a really important difference between these two types of aquifers. In hydrology, we talk about specific yield. So that's the volume that comes out of an aquifer for a unit area. So if we have a square foot or square yard and the water drops a foot, that would be the amount of water that you get out of that aquifer for that. So, for example, if we have 1 cubic foot of water that comes from a 1 foot change over a square yard of the aquifer, that's a specific yield of 10%, 0.1. And again, the yield from confined bedrock aquifers is going to be relatively low. The water yield from unconfined unconsolidated aquifers is going to be relatively high. And the flip side of that is that if we pump the same amount of water from these two aquifers, the water level is going to drop a lot more in the confined bedrock aquifer than in the unconfined aquifer. And likewise, if we put a certain amount of water, if we recharge a certain amount of water, the water level in the confined bedrock aquifer is going to come up more than in the unconfined aquifer. Okay, bedrock wells. So we just kind of talked about some big general kind of statements. When we start talking about sinking wells into bedrock, all bets are off, because basically what happens in these wells is determined by this network of cracks. And unless we do some really serious investigation, we have no idea where those cracks are, how they are connected, and how much water they can hold. And so that's what makes kind of bedrock hydrology so challenging. In this case, we could see like this well here and this well here are tapping into the same network of cracks, so the same water level. If that water level drops below the bottom of this well is going to be dry. So this well is going to be really vulnerable to recharge and pumping compared to this well. Those effects, so the effects of recharge and pumping on a particular well is going to depend on the cracks, and it's going to depend on the elevation of where the well is open in those cracks. And when a well is drilled, it may intersect kind of a series of cracks, and you might not even really know where most of the water is coming from. So that's really what kind of complicates all this. The well itself could, I don't have it shown here, but like if this well was drilled down through here, now suddenly this crack is connected to this network. So yeah, you can imagine this is really complicated. And we don't have a simple model that can kind of account for all this. Yeah. Okay, so we can imagine there's lots of challenges then for managing bedrock, groundwater in bedrock. We have all this local variability that limits our understanding really to where we have wells. So where we have wells, we might have a little bit of understanding, but going into an area, if you drill a well, it's like you're rolling the dice. And even when we drill the wells, we know a little bit, but we still really don't know what's going to happen if there's another well drilled right next to it. Is that going to affect your well? Is it going to even have water? Who knows? The sensitivity of water levels, as I mentioned, to pumping in confined aquifers, that presents another big challenge for managing groundwater in bedrock. We have slow recharge rates. And then we have these thresholds where the groundwater actually intersects the well openings or the land surface for springs. And so if the water level just drops a little bit below your well opening, or which can happen easily in a bedrock aquifer, right? Because water levels are very sensitive just to pressure changes. Or if it drops below the land surface for a spring, now that spring is dry. So these are some really big challenges that, there's not a good way to kind of address this. So the best that we can do in Washington State is, what we're doing right now is guided by a doctrine called prior appropriation. So if whoever has been using water kind of takes precedent because they've appropriated the water and they have rights to do that compared to folks coming in afterwards. So that's kind of this broad doctrine governs water rights, but it also governs domestic wells. Domestic wells are exempt from the requirements for a water right, but they can still impact water availability for existing uses, whether those are other out-of-stream users or else in-stream uses. State policy is to, and again, I'm not talking on behalf of the state at this point, I'm just trying to explain my understanding of this, or interpretation. It's limited, state policy is trying to limit the impact of exempt wells by capping the combined potential consumptive use of water that's withdrawn. And the way it's done is it's done for tributary basins. So we say, okay, in the TWISP, here's how much water we think we can withdraw without impacting other users. The permanent exempt well policies have to address this uncertainty that I'm talking about. And if we wanted instead to kind of like have more certainty, it's going to be really expensive. We're going to have to do like major investigations and very site specific. So we couldn't do like just a really great investigation in one place in the basin and then now we could do a policy basin-wide. No, we'd have to repeat that in every little tributary, and even within tributaries, we'd have to do lots of different investigations. So that's really going to be very expensive, I don't really, that's going to be challenging to kind of try to do that approach. So, you know, these investigations have to account for existing and new water use, groundwater recharge, discharge to rivers and streams. So this is a lot. Like if I had to design something like this, I mean, I could do it, but it's going to be, you know, hundreds of thousands of dollars. And again, it's just going to tell you about one little place. So, so there's a lot of challenges here, and that's what the state policy regarding exempt wells basically is trying to grapple with. So, hopefully that got some people charged up, but in summary, bedrock aquifers provide reliable but limited water in the basin for domestic use and headwater streams. Water levels in these aquifers are sensitive to recharge and pumping, and that's porosity and pressure, right? And water availability varies locally. It's all about the cracks, and so it's uncertain except where we have wells, and even where we have wells, we don't really know all that much. So, with that, I want to thank everybody. I'm glad folks actually stuck around. It wasn't just about the TWISP pub being open on a Tuesday night for dinner. People wanted to hear about water, which is great. But if there's any questions, be happy to entertain them.